Farmer John has lost his prized cow, Bessie, and needs to find her. Fortunately, there's only one long path running across the farm, and Farmer John knows that Bessie has to be at the same location on this path. If we think of the path as a number line, then Farmer John is currently at position X, and Bessie is currently at position Y. If Farmer John only knew where Bessie was located, he could walk directly to her, traveling at a distance of X minus Y. Unfortunately, it is dark outside and Farmer John can't see anything. The only way he can find Bessie is to walk back and forth until he reaches her position. The recommended solution, trying to figure out the best strategy for walking back and forth in his search, Farmer John consults computer science, yada, yada, yada. That part's not really relevant. The recommended solution for Farmer John to find Bessie is to move to position X plus 1, then reverse direction and move to position X minus 2, then to position X plus 4, and so on in a zigzag pattern, each step moving twice as far from his initial starting position as before. As he has read during his study of algorithms for solving lost count, this approach guarantees that he will at worst travel 9 times the distance of X minus Y, distance between himself and Bessie before he finds her. Farmer John is curious to verify this result. Given X and Y, please compute the total distance he will need to travel according to the zigzag search pattern. And then we're going to be given X and Y, and we just got to find, in terms of the zigzag pattern, how far he'll go. So let's draw a number line. 1, 2, 3, 4, 5, 6. We're going to start at 6. This is John, Farmer John, and Bessie. All right, so the pattern states we go to position X plus 1, then we go to position X minus 2, then we go to position being the original thing is going to go to position X plus 4. And since we know it goes beyond, we know that we finally achieved it. So the basic premise is that you're moving to any power of -2 technically. So you start at negative power 2 to the 0. That because -2 to the 0 is going to equal 1. Therefore, you're moving one space. Then you go to -2 to the first, which is -2, obviously, which goes 2 to the back. And we're going to do it so on and so forth from the original position. So knowing this information, let's start coding. Before I move on, any questions about the problem itself? David, any questions?
No.
All right. Time to do the coding section then. Oh, this is a different problem. So, basic format. This format is a bit different because this problem I'm gonna do it in a little bit different way than a regular USACO problem because it's not that we don't need to make it so complicated. So first, we know what do we know? We know that we're given X and Y. So let's get that. And the next in. And then int y is equal to in the next int as well. Now we have X and Y, right? Now we're gonna make a few variables because and I'm gonna explain what they do after I make these variables. Int what 0 s x. Yeah. So what is total? Total is just total. I just abbreviated it because I'm kind of lazy. And total is just gonna represent the total distance we travel. And S is going to be for start, the starting position, for which is X, obviously, because that's where Farmer John is. And diff is going to be the difference. Like I said before, the power of -2 that we're trying to apply. And then we're going to make a while loop. That's true. Because we want this to go on and on until we find a certain condition. And that condition is the break statement we're going to make inside of the problem, actually. So in here, we're going to make int cur. Cur being current, is equal to S, the start part position, because that's the current position. Int next being the next position is going to be X plus mult, because the next position is always not mult, diff is always based on the original position, and then we're going to make a min and max into min to math min. The reason we're making a min max and min is because we're trying to find the distance between these two. Distance between these two to make sure that the position that we need to find is there. Max. And then we're going to check if, and what we need to know is that the position Y, Bessie, if Bessie is between min and max, is basically between these two numbers, then we need to break out of the for loop and print out total. However, if we want to do that, it's going to be complicated. It's going to actually take it's going to take a long time if we make the if inside the while loop, because it's going to take up much more time. So what we're going to do is going to make a method between, I abbreviate a lot of things to make it simpler, between min, Y, and max. This method is basically check if Y is between min and max. And I'm assuming you know how to make a method, so I'm not going to really explain much. And since we want to know if it's in between, we know A is the minimum and C is the maximum and B is Y. So we're just going to be, if A is less than or equal to B, it can be equal. It can be equal. And as we end, because it needs to be in between, B is less than and equal to C, we're just going to return that. Knowing this, we're going to, if this works, if we need to exit, we're going to add math.abs, basically the absolute value. So because we don't need to subtract, because distance is always positive. Y minus current. We add Y minus current to the end at the end for total, because there's a case where you might not go like before. You go from 3 to 4 to 2 to 1 to 7, right? But the position was 6. So you don't need to go all the way to 7. So you only need to go up to 6. So that's why you do math.abs, and then you break out. But if you don't break, what do? You're gonna have to travel to the next position. So to total, you're gonna add max minus min, put parentheses just in case. Max minus min is the distance you traveled, and we know that's never going to be negative because max is obviously bigger than min. And mult is going to be -2. Like I said before, the difference is always like, diff. I keep on saying mult because we multiply. It's going to be a power of -2 because it goes from 1 to -2 to 4 to -8. And just knowing that, it's much more comfortable just going using a power of -2. And start, which is S, is going to equal next. And after we do all this, because it's going to escape eventually, what we want to do is out the println vote. And so let's try this out. I have the input here and the output here. Oh, know that in USACO these days, you don't need to make files because they use standard input output, which is just system.in. So if we were to do this, the answer is supposed to be 9, and it is 9. All right. I'm going to explain this code one more time, and then we'll move on to the next one. So we get scanner, we get print writer like always. We get X and Y. We make total to find the for total distance. We make S for start, which is going to be X initially because we were going to start at Farmer John's position. Then we're going to make a variable called diff. Basically, the difference is going to make the negative power of -2 from the original position. And then we made a while loop that's always true to make sure we only break out when there's when there's like a condition we need to break out. So we make current equals to start, which is the current position. Then we make next, which is the next position, which is going to be x plus diff being once again the difference from the original position. And then we find min being which one's smaller, and max obviously the opposite. And then we check if y position for Bessie is between the min and max position we just found. And then if it is, we add using basically a method. We basically added the position which Bessie is on minus the current. The reason we did minus the current is because sometimes it doesn't go all the way to like the max, and then we break. If not, if we don't break, we add max minus min to total because that's the amount we traveled, and then we make diff the next power of -2, and then we make s the start number next. And then after we do that and break out, we print total. Any questions?
No,
All right, I'm gonna move
following
on,
pretty well, I
David.
think.
Wait, what?
Oh no, I said I don't have questions. I'm following.
All right. Okay, I'll move on. All right. Can you see my screen? I just want to make sure.
Yeah, I can see your screen.
All right. Give me a second. All right. So the next one is gonna be Calnomics, basically. And notice right now, the reason I'm not using system.in is because these problems you can't do that. So unfortunately, we're just gonna have to deal with it. So I have to go with Calnomics. Bovine genomics. Farmer John owns N cows with spots and N cows without spots. Having just completed a course in bovine genetics, he is convinced that the spots on his cows are caused by mutations at a single location in the bovine gene. Each genome is a string length of M, built from 4 characters A, C, G, T, like a DNA. And he's going to line the genomes up. And the potential location is 2 because it's very different. I'm just giving a summary because if you were to read this, it's a bit complicated, and it's just a simpler version is going to make it easier. Basically, we're just trying to find the maximum amount of differences. The first line contains N and M. The next N lines contain each a string of M characters. These describe the genomes of the spotted cows. The final N lines describe the genomes of the plain cows. And we're trying to find the mutation that makes them spotty, so we're going to find the difference, right? Please count the number of positions in the genome that could potentially explain a spottiness. Basically, what it means by mutation, let me just pull out a pen real quick. All right. So look here. All right. If we look here, these 3 are spotty and these 3 are plain. How do I know that? The first N lines are spotty and the next N lines are not. And we're going to compare these. And we're going to find which potentially can make it spotty. Let's look at position. Look at line 1. A, G, G. And then for the spotty cows, and then the plain cows is A, A, A. This cannot be a mutation. Why? Because one of the spotty cows has the gene A, while all the plain cows have a gene of A as well. And if this is true, it's not possible because it has to be totally different. Let's look in second position. AAG for the spotted cows, and for the plain cows, CCC. So this is a potential. Why is that? It's because we don't see a single A or G on the CCC, and we don't see a single C on the AAG. Now, next line. It's all T's, right? It doesn't work. Next line, CTC, and then it's CCT. Both the plain cows and the spotted cows have the same, share something, so no. CGC, and it's CGC as well. They all, once again, share. CCC, CCC, share things. AAA, AAA, share things. TAA, GTT. This may look like it doesn't work, but if you look here, they should. There's 2 plain cows with T and a spotted cow with the T as well. So this doesn't work. So the answer is 1. we're not asking for position number, we're asking for the number of amount of positions. So it's gonna be one. Do you understand the problem, David?
Just
What should
basically
we
looking
do?
for like completely different lines.
Yes, exactly. All right. Time to move on to the
Wait, so are you
coding stage.
gonna
Yep.
like iterate through each one and like make a list of the ones and then see if it's in the list or not for each check index?
Uh, kind of not. I'm gonna show you like a much more efficient way.
Okay.
So yeah, if you see here, I left the variables that I'm going to make up here. Uh, they don't really mean anything yet to you, but I'll show you why. Except for file name, R. This is a different way of making the scanner thing, but you won't need to know that since you're going to do system data anyways. Anyways, let's in it for initial. We're gonna make the int. So we know we have n. We need n int. We're gonna take in the next int, and then we're gonna get a, which is gonna equal in that new int n. So what are we doing? What are we doing? You might be asking. Well, it'll be clear because this looks very actually no, not in the next int. I have made a small mistake. Right, since you're oh, I'm on the wrong one. Sorry. That's on me. That's on me. It might have been a little bit confusing there. I'm sorry. Here. These
Okay.
are the variables I want to use. I knew something was fishy. So we see we have a buffered reader. This is just a faster scanner. So we're gonna make a string tokenizer because that's what we need to do. St equals new string tokenizer and line. And what the string tokenizer does is literally get the entire line. So, and then we use in our inline. And the reason we use string tokenizer buffered reader is because it's faster and we always can save time on USACO. And then we're going to do integer.parse int st.next token. Next token is the same thing as in.next. And we're going to do that the same thing for m. And then we're going to make two new 2D variables, not 3D, new char and then empty. The reason we made it empty instead of m is because we're going to just do in that readline dot to char array. And if it's there, it's probably not going to work. So we're going to make s for spotty and p, the same thing for plain. And I want you to know that you should name variables that are easy to remember what it is, because if not, it's going to be really confusing. So for int I is equal to 0, I is less than n, I plus plus, s at I, basically at row this, what you should do is in that read line, and then turn that into a char array. And we're actually going to do the same thing for p. And then, yeah. And then now we're going to go into solve. Within solve, we're actually going to keep it very simple because what we're going to do is we're going to make a method where we're actually going to plug in number, make a Boolean array that holds whether this or this gene has this gene, which genome has each gene. My bio terms are very lacking. So we're going to actually use a method because that's much faster. So to do that, my answer for int I is int j actually is equal to 0. J is less than n because we're going to parse through all of them, all of these, what is it called? Genomes at once. And we're going to use n to our advantage. And we're going to put j plus plus and if check at j. So what is check? Check is literally, like I said, it's going to check if it's the same or not. We're going to do it in method because it's once I show you what we're going to write in the method, it's going to be abundantly clear why the method is much faster. And we're going to add one to ands, and once we get ands, we will print it out. So let's make check. Static Boolean. We're gonna, since if you see here, it's if check, not if check equals to something. So if Boolean check int j, and then what we're going to do is has gene. We're gonna make this thing called has gene. Basically, it's gonna check if it has a gene. Equal new Boolean 2 and 4. What are we gonna do? We're gonna make a few for loops that check P, S, and P whether they have a certain gene at this certain M at this certain position amongst M. So for int I
Wait, can
is
you
equal to,
explain lines 50 and 51? I'm not super familiar with Java.
oh, you're not familiar with Java?
No, I use Python, but like I know the
Ah,
basic
so
concepts.
50 is just making a new method
Like a
and
function.
in I think in Python it is a function.
Okay.
And line 51 is has gene is just a name of a 2D array that I established.
Okay, so it's just a 2D array.
Yeah, it's just a 2D array. It has gene made it seem like it's something special. No, it's not. It's just a 2D array. That's it.
How about
Uh,
new Boolean?
a new Boolean is how you established an array. If you see here, new char, uh, that's how you just establish a what is it called? An array in what's it called?
Oh,
Java.
okay, okay.
Like if it was a
hmm
1D array, it'd just be like this. But since it's a 2D array, there's two. That's about it. New
Okay.
Boolean literally means new Boolean array. The
Oh, I
good thing
see.
about, yeah, about Java is that you can take some things literally and you can just be like, oh, I see what it is. And then we're gonna make a for loop that basically checks if at this position of J amongst the S, does this thing have this genome? And which genomes does it have? Basically, it's just gonna, because you know how we have a multitude of spotted cows and spotted cows. What we're gonna do is we're gonna check if it has A, C, G, and T. We're gonna check which one of these it has and which one of it doesn't have, and we're gonna do the same thing for P. So if S at I, J as in the thing we got, is equal to A. The reason we made it into char array is because we can use equal equals instead of dot equals, which is a headache. Has gene 0, 0, 0, 0 being, this is like where we just kind of like gotta assume things. True. We're gonna take row 0 as we're going to take row 0 as A for S. No, we're going to take row 0 for S and position 0 as A. And we're going to do the same thing again and again. 1, 2, 3. And instead of A, it's going to be C, G, T. And then we're going to change 1, 2, 3. And the reason I kept 0 the same, like I just said. Row 0 is for S. A is going to be at position 0, 1, 2. And let me just show you in terms of a table. It's going to makes more sense. So we have S and P, right? S and P. That's why this is 0 and P is going to be 1. And then we have A, C, G, and T. And what we're doing is basically at among the spotty cows at this position, is there an A? We're just checking true, false, and then P is like false, 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 true. And basically we're just checking, hey, does does anything correspond? And we see that if T were to correspond, then we return false because that means it works. And if not, if none of them correspond, that means it does not work. So we're gonna have to return whatchamacallit, true. So instead of P this time, it's gonna be S this time, it's gonna be P. Ooh. And I'm gonna change this to 1. And then we're gonna make another for loop. And this is only going to be up to 4. Why is that? Because there's A, C, G, and T. There's only 4. If as gene, if both S has it and P has it, then return false. That means, oh, they both have it. So that means I don't have to add 1 to ants. Else, return true. That means I have to add 1 to ants because there is a significant difference. And after that, you just print out ants. And if we try it out, voila, 1. So I'm going to explain everything again. We started by making a string tokenizer. Why is that? Because string tokenizer is simply faster. Then we made M and M. Then we made S and P, S being the spotted cows and P being the plain cows. We filled them up with char arrays because we can use equal equals, and that is much more simple. And so we made ants to count how many of the mutations are possible. Then we made a for loop that uses M. Why did we use M? The reason we used M is because we want to traverse through all of the arrays at the same time for each position using a method. And why did we use a method? Because it's faster. And we called it check. And if check works, we add 1 to ants because we're checking if there's a mutation or not. And then within the method of check, we take in the variable j, and then we check. We made this 2D array called hash g. Row 0 is for S, and row 1 is for P. And column 0 is for A, column 1 is for C, column 2 is for G, and column 3 is for T. And why is that? We're checking amongst all the spotty cows and plain cows at their respective positions. Do they have an A? Do they have a C? Do they have a G? Or do they have a T? And that's what the next 2 for loops are for. They're checking if they do have it. And if they do, we put the thing to true. And then we make another one. We check at position I at S and P. If they're both true, that means if they share something, that means it cannot be a mutation. So we return false. However, if it never returns anything, that means there has to be a mutation and it returns true. And then afterwards, you simply print out ants. Any questions?
No, I like this approach.
Okay, yeah. Yeah, because instead of parsing through everything, we're technically parsing through everything still. Yeah, we're doing it all at once. We're looking at everything at once. So it makes it much faster and much less of a headache to look at. All right.
Wait, are you doing the chart you drew earlier?
Yeah.
Are you doing that for like each iterating through each like
Yeah, for
I don't know what
each
you call it
column,
like
that's what
the
I'm doing.
okay.
Yeah, so basically, let me just pull up the problem. You see here, what I iterated through basically was the reason every time the method went in, it would look at this, like this entire thing, and then it'd make the table. So did I put S first? Yes. S and then P, A, C, G, T. And then I check for S, which is the spotted cows. I look, is there an A? Yes. And then I look again for the next one. Is there a C? No. Is there a G? Yes. Is there a T? No. And then we move on to the plain cows. Is there an A? Yes. Is there a C? No. Is there a G? No. Is there a T? No. And then the last for loop just checks, hey, a common one. And then there is a common one, so we return false. However, eraser. If we look at row 2 here, there's an A and there's a G. And in the plain cows, there's a C. We have nothing in common. There is nothing in common except for the fact that it's empty, which doesn't really matter, and we return true. That was basically the entire problem.
Did you use like a loop to check if it had anything in common?
Yeah, this
Or
final loop was just checking if there's anything in common.
okay. So what's the
Yeah.
time complexity? Because I always get like time complexity errors. It's like a few
Yeah,
times.
that's the reason we use the method and a string tokenizer. Because it's much, much faster. And instead of parsing through everything, we're technically only parsing through one position at a time. So it makes it much, much faster.
Okay.
Yeah. All right. We're going to move on to the next one. This one is called art. I kept the basic things. These are going to mean nothing to you right now, but they will mean something in a second. This one, in my opinion, was the hardest one. All right. Time to pull that up. I hated this one, honestly. Our critics, I'm going to skip the useless information. Picasso paints in a very particular way. She starts with an n by n blank canvas, represented by n by n grids of zeros, where a zero indicates an empty cell of the canvas. She then draws 9 rectangles. 9 rectangles, one in each 9 colors, numbered 1 through 9. And an example, she starts by using 2, then 7, then 3. And we see something is the fact that the later colored ones overshadow it like this. So this is going to be important. Each rectangle has a side parallel to the edges of the canvas. That means it's always perpendicular and it's so much easier. And a rectangle could be as large as the entire canvas or as small as a single cell. For each color, 1 through 9, is used exactly once. Although later colors might completely cover up some of the earlier colors. Basically, there might be like a single-celled one, and then there might be one that covers the entire thing, so you can't see the original one. Given the final state of the canvas, please count how many of the colors still visible on the canvas could have possibly been first to be painted. And so basically, we're just finding which one could have been on the bottom after being covered. So, yeah, we see here we're given n, and then we're given the canvas. And then we only see one because the only possible color is 2. Because 3 had to be painted over 7 and 2, obviously, because 7 is covered and 2 is covered. And if we were to take out 7 and 3, basically, there'd be a 7 here and there'd be a 2 here because it has to be a rectangle at all times. Knowing this, we know that 2 is still covered. So 7 has to be removed, and the only thing that left is 2. And we're going to code that. That sounds extremely complicated, and it was kind of complicated, but I'll explain to you. Like before, I'm going to go kind of like just code only first time, and then I'll explain it in more depth after I finish. So, what do we do first? We get n. We always get n first, usually. It's like one of the best first steps in musical. And then we establish A. What is A? A is the canvas. And then we made min x min y, max x, max y. And why did we make min x, min y? It'll become much clearer later on. I just want you to look for now. Because some things, even if I explain, don't make any sense. And it's just better to sometimes see what it does in action before I explain it. It'll be much more convenient that way. We made 4 min x, min y, and max x, min y, max y. And we're going to fill all of them. Array that fill min x, comma 10. Min being the reason we do 10 is because the maximum it can go to is technically 9. And it's just much more convenient that way. And we're going to fill all of them. Not with the same thing. Max x is going to be full of -1 since it can't be -1. Min y is going to be 10. Max y is going to be -1 once again. Oh, one quick question. Do you do the USACO competition like through Python or through Java? David.
Go to Python.
Oh, you do Python. I don't know if this is very helpful, but one thing you can get away, even if the code is not the same. I used Python before too, so I know the basic gist. You can use the same idea to code it. The format isn't like it's not also different. So you should be able to use like the basic idea and the format of it.
Yeah, I'm
So
just
we're
like
gonna
trying to like
yeah,
get like your approach and stuff because I always get like time errors.
yeah. Oh, time errors are so annoying. As a as a person who've done music for several years, time errors is gonna be your worst enemy. Your number one enemy is the problem, and your number two enemy is time. So Yusuko, your life depends on the fact that you gotta make it as short as possible. And that's not always easy. But it's something you gotta do. So we make char C. Char C, this is just a temporary thing. Char C is equal to in the next being the next line, to char array. And the reason I did that, give me a second. Chrome is in the next we'll get the entire thing, and it's gonna step two char arrays and separate individually. So it makes things much more simple. So we got char C, right? And then within this larger thing, why would you do that? Why do you put me like this? For int j is equal to 0, j is less than n, j plus plus int num is equal to c at j minus 0. This is basically changing the what is it called? The character back into a number, and the reason we did -0 in the single quotation marks is we're removing the what you call the ASCII values at this point. So there's a big complicated things. Just yeah, a at j is going to equal to num. Basically, we're putting it back into I, a at j, and this is where min x, min y come into play. Min x at num equal to math min x at num I being the current like position or aka like color. So knowing this, we're going to do the same thing again. Y max x. We gotta check all of them because that's the way it is. And for y, we're going to use j. Seems I've made a little error like this. I'll explain what max and I and j do a little later because I want you to see what they do before I explain it because to be honest, I can kind of explain it in a kind of confusing way, so I don't want you to be confused. Paint. And what are we going to do at paint? The reason we are adding to paint, which is an array list, is because we're saying, hey, paint is going to hold all the possible paint values that we're holding. And if it's not zero, put it in. Because zero can't be a paint number. It's got to be zero from to -9. Then we did all of this. We're going to solve now. It looks like we did a majority of the work in init because init is unusually long right now. And you're not wrong. You did do most of the work in init. We're going to go into solve for I is equal to 0. I is less than equal to 9. Is less than or equal to 9, or you can just say then I plus plus, and then max if max x at x, I is equal to -1, because the max shouldn't be a -1. If it is -1, that means get out. That means nothing was painted. It's just continue. And then, well, max x is just like nothing was painted at that certain color, so get out. At that certain box, my bad. For max int k is equal to max j is equal to min x at I is k is less than equal to max x at I, because we want to go I type k on excellent all the way to I, and then we're going to add 1 to j, and then we're actually going to copy and paste this because we want to make a nested. We'll change all these variables, k, y. And basically, we're just going from the minimum x and y position to the maximum x and y position of that certain color, basically. And then if a at I at j is not equal to, actually, is not equal to I, if it's not equal to the color, and then paint that contains a certain color we're talking about, I at j, you got to remove it. Paint that remove a at I at j. That's basically saying this cannot be a first color because it's covering a color. And then once we do all of this, out the println and paint that size, because it'll leave us remaining the amount of possible first colors. And then if we were to run this, there's a null pointer exception where I have made a small error. I forgot to initialize paint. And then if we were to do that, why are you doing this to me? Why? Oh, always check your variables. Always do that. I suggest that. I'm an idiot, so I always forget that. These little small things are gonna sometimes take you forever to find when you're doing USACO, and it's the most annoying thing ever when you can't find it. Anyways, works now. No, it doesn't. That's annoying. Give me a second. I'll just review my code real quick. I see the problem. Ah, I'm stupid. Yeah, you start at one because all the paint colors start at 1 through 9. I have no idea why I put 0. These small things will hurt you, like I just said and showed you in person. Anyways, David, we're gonna start from the top. We got N because that's the best first step. Then we initialized A, which is basically the canvas. And then we got min X, min Y, max X, max Y. Why did we do that? The reason we did that is because, hey, what is the maximum and minimum X and Y value for each of the colors that we're looking for? Basically, the corners. And then we basically went and got the board one at a time, filled in the board, and then we got the maximum X and Y for the individual color at that color. So, and if none was not equal to 0, basically saying if there is a color there, add it to paint because paint is going to hold all the colors that we used. And then we go to solve. And within solve, what do? We check max X. What do we do at max X? We check, hey, is this color exist? Because max X holds the maximum X value for all the colors. And it says here, oh, hey, look, there's no max X, which is -1. Then we just continue on. If there is, we go into another nested for loop. That goes from min X to max Y, min X to max X, and min Y to max Y. Basically, we're checking the entirety of that color's corner, from corner to corner. And then we check, hey, at this position, if there's if it's not equal to this color, and this color is within A, I mean, paint has this color, then remove it from paint because it can't be a first color. Because if at this position we're checking for like color 1, but we find a color 2, that means color 2 is covering it, so it can't be a first color. So we get rid of it from paint. And then we go until we just for loop that, and then at the end we print out the size of paint. Why? Because the size after we do everything, anything that can't be a first color will be eliminated. So we have paint that size. All right. Any questions?
So are you basically like for each color you're finding like the corners and seeing if like the rectangle is like full so that's like the first one colored?
Uh, so basically, what we're doing is we're getting the corners of every color like this
Yeah.
and stuff.
Mm-hmm.
This is going to be max X, max X and Y here. No, this is going to be max X and minimum X and Y. And the max X and Y for this case, at this case, is going to be here because the max X is here and the max Y is here. So we do that for every color, and then we check, hey, we're going to go from 1 through 9, basic colors 1 through 9. Since the first color that appears 2 right here, we're going to look, we're going to go through max, we're going to go through X and Y. So we're going to go da da da. It's going to go da da da. Okay, fine. Da da da. 7 appears. Oh no, we can't do 7. We know the paint is holding 2, 3, 7. We know, hey, it can't be 7. Cross that out. And we do the same thing for like 3, and it's like, oh shoot, can't do that. And we eliminate it and we left with 2. That's the premise of what we just did.
Why are you eliminating?
Why am I eliminating? Because the problem asks for the number that could have been first painted. And if we look here, if we get rid of 3, that means this has to be 2 or 0 or something else. And this has to be 7. And knowing this, 7 had to have covered something here. So it's got to go like this. And only 2 could have been the first color. Does that make more sense?
Yeah, I get the problem. I'm not super sure how you like coded it out.
Oh, okay, I'll show you. This one, not my favorite. So basically, literally, what we did is we found the minimum X and Y for the corner and maximum X and Y for the other corner. And
That's
then what we
the
did is we
entire
filled in,
canvas, right?
Yeah, for the on the canvas, for all the colors on the canvas. And then
Mm-hmm.
we found the color. We looked through the entire thing and we looked for the colors that were possible. And then we found a color, right? And we add that to paint
Mm-hmm.
because we're gonna be like, hey, that's color. And then we check, is this the corner? No, it's not. So we just keep it here like this. This is basically num is basically the color, and min x and min y are just the reason it ranges from all the way to 10 is because we gotta get 1 through 9, and we don't want to use 0 and use minus minus, which is a hassle. So hence this. And then we come down here and we check, hey, does max x have anything? Because if max x is -1, it means that color didn't appear. So we simply just go like that. Max it I. And then we see, hey, we go into for loop and we go, hey, at this point, if it's not equal to the color we're looking for, because what we're going through is basically the corners. We're using the corners. We're going to go through like a rectangle. Hey, if there's a thing that appears and it's not supposed to be there, we should delete it. And hence the not equal to I, because I is the color at this point, and contains A at J at K basically means if it's not the same color and paint has this color saved, remove that paint from what is it called? From paint, because that color cannot be a first color because it's clearly overlapping another one. And we do that over and over again until we run out. And then we go out and we're like, print out the size of paint. Because whatever is the remaining numbers are gonna be what is it? Colors that could have been first. Does that make more sense?
Oh, okay. Yeah, I see it now.
Yeah.
Yeah.
Yeah. Yeah. Because while I'm like typing, I can't really type and explain at the same time, so I gotta do it separately. So yeah.
No, you're good. That was a good explanation. I was confused for a second, but
Yeah. Thank you.